All right, well, thank you very much, Russ, and thank you very much, everyone. So first of all, I'm here because Yasaman graduated, so this is sort of like the last postcard that Yasaman is sending to Metal Earth to give you a little bit of the context of what the work that she's been doing. So it's a very long title, but basically we're going to look at a little bit more precisely how different alteration mechanisms might be we might be able to find them within our borehole data and how it might actually help us with exploration. And so at today's gold prices, I looked last night and they're still over $5,000 American. So the question, I always tell my students, the first thing you need to do is find the right question, right? And so what is the question? Well, at the gold prices is where's the gold? Okay, so well, I'm not sure that I can necessarily tell you exactly where the gold is, except that there's a lot of people looking for it. And one of the things that we can see is that our discoveries are decreasing. So it's probably time to try to do things differently a little bit. Okay, so other sayings is that the gold is where the gold is. And so, well, if you're going to look for gold, it's probably a good place to go where you found gold before. So this project is looking at the Abitibi. In particular, along the Cadillac-Larder Lake Fault. It's at Yorba Resources. And Mustafa was saying that in the oil and gas industry, normally you would have these boreholes that transect and then you can do your ties. We weren't going to go to like 5 kilometers, but our plan was actually to go down to the first kilometer and try to map these things to at least give confidence in the first kilometer. We actually started our project a little bit too early because we went and logged some holes, but the seismic transects never reached us. So everything that we did for seismic, we tried to do some BSP and different things like that, but it was not any use because we never got to Hawaii. So some of the data that we've looked at, it looks a little bit like this. So I realized there's a lot of columns here. The important thing to remember is that we can measure a whole lot of things in boreholes. Which ones are important? Well, it depends what we're looking for. But one thing that we know, well, and I'm a geophysicist and even I know this, is that gold is associated with quartz veins. And so when I look at my OTV data and I see white stripes, well, I say it could be quartz veins or carbonate veins, so there's good chances that I might have gold in that. We also look at the gamma ray. And gamma ray is basically just like having an idea of how many gamma particles are generated. They're naturally occurring. In this case, the reason why gamma ray is kind of useful is because it allows us to decide if we are in the Pichet group or not. And so one of the first things that Yasaman discovered is that some stuff was logged like Pichet, but it wasn't in the Pichet, and we could separate that data because of the gamma ray. So already that was a good contribution. So everything else that you see, like the computed density that we had, the shear modulus that we calculated, and the seismic impedance, it was all good, but again, couldn't contribute to any regional seismic because the seismic didn't reach us. So what you'll notice is also that these quartz carbonate veins, okay, in the image they look kind of similar, but their response is different. So we have to try to understand why the responses are different and what that can tell us. The model that Yasaman pursued is a model that was published by Dentit. It's a ternary diagram, but basically we go from trying to understand what the physical properties, how they affect what we can measure. On the top here, we have what we've seen today, so density. Okay, so those are really related to changes in the bulk of the mineralogy that we have. And then we also saw today that we have magnetic susceptibility or magnetic fields. And that's really related to like the inclusions of magnetic stuff in our rocks, okay, like magnetite, for instance. So where do we start? How can we actually, what sort of alterations, what would alterations do to our rock? And how might it affect our petrophysics? So 2 types of alterations that we can find. Well, we've got these formations of quartz carbonate veins, and we've said that those are usually related to gold, so we'll concentrate on those. But we can also have alterations that bring sulfidation. And so let's see if we can actually find these in our data and try to track them in space. So the first is the quartz carbonate. And we saw that there's a lot of texture related to the quartz. And so there's a good idea that electrical resistivity might actually help us out here. And so before I show you data, I thought it'd be interesting because you'll see these N8 and N64 mnemonics, and it's good to understand what we're measuring. And so in this case, it's a borehole tool. It's probably one of the oldest borehole tools for geophysics because it was made by Schlumberger. It's basically just putting like an electrode down there and measuring potential, okay? And so when we talk about N8, it's just that the potential electrode is 8 inches from the injection electrode. And when we talk about 64 inches, it's because it's 64 inches from the injection electrode, okay? So the only thing that differentiates the data that you see at the N8 and N64 is just the separation of the potential electrodes. So if we go back to just normal oil and gas logging, this is what our tool would look like from Ellison Singer. So we have our injection electrodes here that are A and B, and we have our potential electrodes, which are M and M. Anybody done wireline logging in the oil and gas industry before? Because I have to deconstruct kind of things, no? Okay, so like in petroleum, you have something that's called the invaded zone. And so usually when you try to measure in these reservoirs, you've got this RI business where the muds have actually made their way a little bit in the formation. Here, we don't really have an invaded zone because we don't have open fractures. And so our boreholes are clear. Really what we're seeing is just the contrast between our borehole fluids and the rock, okay? So keep that in mind as we go. So the next thing that Yasaman did, well, she thought, okay, so since quartz veins are important for gold, let's count the number of quartz veins that we can see on our OTV data. And to be able to actually normalize that, she's multiplied it by the thickness of the veins. And so what we can see is that for the length of the Pichet, the number of quartz veins really increases from the image. But then if you actually put the N64 data on top of that, you can see that the electrical resistivity also increases. So many of you will say, well, okay, well, yeah, we knew that quartz is resistive, so good job. Well, it reassures me that we find something resistive where we expected to find resistive, so that's a good start. Second piece of the puzzle, though, is that when we start looking at the N8 data, so the data that's where the potential electrode is not as far, we get these strange patterns, okay? And originally, when we started looking at these data, people told me, I think the N64 just doesn't work. The tool's broken because the values are always very different from the N8 data that you pull. We actually looked at the calibration of the tool every time. We know that the tool is working. So it is measuring something in the rock, but we just don't know exactly what it is, okay? Now we know, okay? So what we're gonna look at is that, oh, I'm being attacked by bottles of water. What we're gonna see is that the quartz carbonate veins actually correspond to these red points that you see here. And areas where you have sulfidation or where you haven't had any of these alterations, these are these green points that you see, okay? And so we're back to our question is, where's the gold in this? And I've told you that this is quartz carbonate veins. And so if we actually start coloring by gold grades, what we can see is that we have like these blue dots and green dots that correspond to my highest grade gold grades, okay? So we can see that in these resistivity structures, the apex of these curves seem to correspond to our highest gold grade. These 0 to 1 grams per ton are in the way, so let's take those out and just look at our gold. And so we can really clearly see where these are landing. Okay, so now we have a way to see that they're associated with the resistivity peaks that we see in our data when we compare the N8 and the N64, but why do they have these shapes? Okay, and so what Yasaman did, she did a lot of finite element modeling to try to understand these curves. And this is the result of it. In that, imagine the tool that we saw previously. It's coming from the bottom and going towards the top. And so here, when we're next to the one-to-one line, so the two sets of electrodes are measuring the same thing, we're not actually in the vein yet. As soon as we start sensing the vein, so as soon as the electric field gets distorted by the vein, we start to get this excursion between what we measure on the N8, which is the green line here, or the turquoise line, and what we measure on the 64-inch. And so this is how we actually start getting this separation and also this S-curve that we saw appear previously. What's interesting is that when we get to the top of the curve here is actually when we're in the middle of the vein. So we can see that where we were looking at, where we had the highest gold grades right now, are associated with the middle of the vein. And then as we exit the vein, or the tool exits the vein again, then we come back down along this curve, okay? So all of a sudden, just by looking at these two resistivity signals, we can actually have an idea of how pervasive are quartz veins in this area, and other little factors that can be associated. Now, this is the type of modeling that she's done, and it wasn't really intuitive originally, in that we thought that all of the current was probably going through the borehole fluid, but it turns out that this resistivity structure is actually shielding our electrodes once they're actually on the other side of the vein. And so this is why we're getting some slightly strange values, is because there's not that many electrical field lines that actually get past this resistive vein. There's a little video, but we don't really have much time, so we'll just go and keep on going. So we looked at, okay, well, what really affects what we're measuring then? Is it the vein radius? So the vein radius is being like if you want, how wide it is on either side of the borehole. And we can see that it doesn't really change very much our curve, right? So what this tells us is that we don't really see that far in the formation with this type of tool, okay? Second thing is the angle effect. So we've tried to take this lens or this vein and try to change its angle. It changes a little bit, but it's not really diagnostic, okay? So what makes a big difference, or starts to make a difference, is the vein thickness. So the thicker it is, well, the higher this peak is going to be, okay? And then finally, the vein resistivity effect. So when you start changing the resistivity of the vein, of course, you can actually make it change. So more or less resistive veins are here, and the more resistive your vein becomes, the more you get this excursion towards the right. But the one that has the most effect is actually the borehole to fluid contrast. And so this is important because traditionally in the mining industry, we've never really measured the conductivity of our fluid. We've basically just assumed that it was relatively fresh water, and we just went on and logged. But we can see that this can have a significant effect. So if you take one thing about my talk today, is that when you do normal resistivity surveys in your boreholes, you should acquire fluid conductivity at the same time. Okay, so well, you'll say, okay, well, but you've done finite element modeling, that's fine. All kinds of people do this, but can you reproduce real data? And the answer is yes. So Yasaman went back to her data. She found this event, which corresponds here, we can see here, it's a succession of veins over 14 meters or 550 inches for, yes, people in America. And so we've modeled this data and we get something that looks like this. So we can see that we don't necessarily have all of the complexity, because here all we're doing is putting like an apparent resistivity for the vein, but we can see that we can reproduce the shape. Next thing that's interesting is we take all of the boreholes that were acquired in this area, and we can see that they all have slightly different shapes. The first thing that'll jump out at you is that you've got these orange points here that all follow this one-to-one line, okay? And so we would expect that this borehole corresponds to an area that's probably hasn't seen the formation of veins, and then the other ones, we might have actually seen them. And so if you look, this is the cross-section at Yorbo, and you may have, yeah, I think the next, no. So you have these little stars that correspond to where the pichet is and also the endowment of the pichet. And you can see that this star that corresponds to Busan is the area where we have this these orange data sets. Okay. You might say, okay, well, neat party trick for all your friends and geophysicists, but can you reproduce this somewhere else? And the answer is yes. So this is another sector that we have in Northern Ontario, and we can see these shapes being reproduced. Can we see other things, other effects from quartz carbonate veins? Yes, and the thing that we were talking about this morning, so seismic. So we can see that as we actually introduce the quartz carbonate veins in the matrix, the rock becomes stiffer, and so the VP and the VS increases. So this is relatively well seen here. And then how about sulfidation? Because I talked about sulfidation a little bit earlier. Well, it turns out that if you look at the little metal grains that you have in your rock matrix, it reacts quite differently. There's two different ways we could actually measure the effects of these little grains. There's the IP method, okay, where you'd have an IP response because of disseminated grains. So this is what we have on the y-axis. And you have the SP method. And SP here is self-potential. And so what we discovered is that the areas where you have sulfidation, or I should say we rediscovered from the Russians, because eventually we found a literature link for that, is that the areas where we have sulfidations are the areas where we have these large negative SP anomalies. And so when we are in areas where we don't have these sulfides, we have like positive values. And so finally, the way this is explained is that when the holes were drilled, surface water was brought to depth, and there was oxygen dissolved in this water, and it starts reacting with these sulfides. And this is how we end up having our SP data anomalies. So in the end, if we ask the right questions, we can learn to see the world differently. And I always maintain that Charles Babbage was right, which is that errors using inadequate data are much less than those using no data at all. And so on that, thank you very much.